Hello, or today's video is about FRSICL, LLM-Enabled In-Context Learning, Flight Resource Allocation for fresh data collection in UAV-assisted wildfire monitoring. This video introduces a new online flight resource allocation scheme based on LLM-enabled in-context learning. This FRSICL jointly optimize UAV flight control and data collection schedule along the trajectory in real time to minimize average age of information. My name is Yusuf and I'm going to present this video. Okay, here you see the outline, introduction, overview, communication protocol, proposed algorithm, result, and finally I present the reference. Okay, introduction. As you know, the common trend in UAV assisted wildfire monitoring for optimization is using deep reinforcement learning. But deep reinforcement learning has some challenge such as low sampling efficiency, simulation to reality gap, and complex training. This feature makes deep reinforcement learning unsuitable for wildfire monitoring. We need quick and prompt action. These concerns are relevant in the context of the online deep reinforcement learning, where models need to learn and adapt in real time, which may not be feasible in urgent emergency scenarios. Okay, what is the solution? In such a situation, in wildfire monitoring, we have to use in-context learning. Please watch my previous recorded video on in-context learning to better understand the topic. This video proposes the onboard flight resource allocation scheme for UAV using LLM-enabled in-context learning to minimize the average age of information of ground sensor. Okay, here you see actually our view of the task description. It has some component, task goal, input data, role and constraint, output, feedback, and system prompt. Here for FRSICL, the task goal is optimizing data collection schedule and velocity to minimize average age of information. The input data is the current average age of information, channel condition, and UAV location. We have some role and constraint, prioritize sensor with high AOI to enhance data freshness, or output is sensor activation schedule. We have a feedback loop that play a critical role in the in-context learning. It records LLM decision, environmental state, and system performance, and guide the future decision. Okay, we have also system prompt that specify the role of the LLM, for example, to follow safety rule and ethical rule. Okay, we have a UAV, we have some ground sensor. UAV interact with ground sensor, collect sensory data, submit data to LLM. LLM shape a task description, and based on task description, make a decision and return back to the UAV. And this operation continue until the end of the mission. Okay, here you see the communication protocol for FRSICL. We have some ground sensor, we have a UAV, we have a large language model. UAV collect sensory data and then run FRSICL in collaboration with the LLM to schedule the sensor. Then the scheduled sensor collect data and send back to the UAV, and UAV send the acknowledgement for it. Okay, here you see the proposed algorithm. We have a one main loop. UAV sends the environment and collect data. which are current age of information, channel condition, and UAV location. This data is transmitted to the LLM. LLM prepare the input and shape task description and generate data collection schedule and velocity, and UAV execute this command. Okay, then we have feedback collection and updating LLM with feedback, and then go for the next round of the operation. Okay, here in this slide, you see the obtained result that show the performance of the FRSICL. The blue line is FRSICL with O3 mini language model in comparison to the proximal policy optimization. As you can clearly observe, the FRSICL achieved better performance in comparison to the PPU. Also, FRSICL that is with O3 Mini achieve better performance in comparison to FRSICL with 4O Mini. Okay, O3 Mini achieve better performance in comparison to the 4O Mini. And in this figure, we have increased the number of the grand sensor. By increasing the number of the grand sensor, age of information increase. As you can see, the proposed approach, the blue bar, achieve lower age of information in comparison to the nearest neighbor baseline. And in this figure, you see the age of information of each sensor in comparison to the proximal policy optimization, and we achieve lower age of information in comparison to the PPO baseline. Thank you. This is my reference. You can find the version on archive, and I appreciate your attention. I would be happy to like and subscribe.